Today we're going to be going over parts of Chapter 4, which covers both glaciers and arid or kind of desert environments. But for the sake of time, we're only going to focus on half of this chapter on the glacial landscapes. But before we begin, we need to discuss exactly why are these glaciers so important when it comes to Earth science. And we'll see that the amount of glaciers on our planet have changed tremendously throughout geologic history, but our glaciers also have really big, important roles in both our water and our rock cycles that occur along the surface. So, when it comes to a glacier is just a really thick chunk of ice. So, if you were one of those people like me that really got into Game of Thrones, think of the wall, where we're talking about hundreds to thousands of feet thick ice that form. But glaciers take really long periods of time in order to form, generally hundreds to thousands of years, because glaciers form in a very specific way where we have snowfall accumulating. So we have snow just very gently coming down and hitting the surface. Since it's a cold environment, that snow is going to stay within this layer. But over time, more and more snow is just going to settle down on top of it, which is going to begin to compact it. All of that weight of the snow is just going to push it down and compact it into a smaller area. But as each individual snowflake is being compressed, it's going to cause that snow to recrystallize. It's going to turn it from loose piles of snow into thick, solid pieces of ice. But this entire process, again, it takes a very long period of time in order for a glacier to actually form. But once glaciers actually do form, they don't just sit still. They're constantly flowing, and they generally move downhill just like a river does. But when we're looking at glaciers, they move incredibly slowly. Most of the time, we're talking about a few centimeters, far less than an inch, every single day. But just like a river, we're going to see that as our glaciers flow, it's not only the ice itself that's moving, it's also going to be eroding some of the sediment sitting beneath the ice, and it's going to carry that eroded sediment somewhere else, and then eventually deposit that sediment on the ground as the glacier melts. And we'll talk later, but during our Quaternary period of Earth's history, in the last 2 or 3 million years, we see periods of time where there's a lot of glaciers, and then we see other periods of time where there are very few glaciers on the Earth. But we'll see that times when we have a lot of glaciers or just a lot of ice covering our planet, we generally term these ice ages. And if you've ever seen the animated movie Ice Age, it's actually fairly correct scientifically. There are times throughout our history where we see enormous portions of the Earth just completely locked into solid ice. But when this happens, we're going to see that our glaciers have really important roles because glaciers, they're just giant chunks of ice. That means that all of the water that's stored inside of the glaciers is going to be trapped there. Because this water is now a solid, it's not going to be able to just quickly evaporate and go back into the atmosphere. As long as that glacier is still there, all of the water inside of the ice is going to be stuck there until eventually the earth warms up a little bit and that glacier melts back into liquid water. But we see that glaciers are also really important when it comes to weathering. And just a reminder that weathering is when we're breaking down rocks along the surface of the earth. And we see that ice is really good at mechanically weathering or breaking down rocks along the surface. And we'll get into this some more as we go. But we're going to start off by going over some of the general types of glaciers that we see on our planet. And the first one is called a valley or an alpine glacier. And the words are basically used interchangeably. But these always happen in really high mountainous regions, like we can see here in this image. But here the glaciers are going to be stuck in the valley of these mountains. So if you have two mountains that are side by side, your valley is going to be this lower portion where all of the snow is going to accumulate and eventually turn into solid ice. But these valley glaciers found in our mountains are generally very small glaciers. And this is because they're stuck between two mountains. Therefore, they're going to be very narrow in their width. They're not going to be able to expand outward because those mountains are trapping it in a low-lying area. So we see that these valley glaciers are generally very narrow in their width, but they're very long. They generally start at the very top of the mountain range and then sometimes can work all the way down to the base of the mountains. But just like a river flowing down a mountain, we see that these valley glaciers also flow downhill. But unlike a river, glaciers flow very, very slowly. Again, we're talking about maybe centimeters per day. So it's not like a river where we can just go watch water flow through. With these valley glaciers, we're going to need to set up cameras and take time-lapse shots that are days to years apart to figure out exactly how fast glaciers are flowing down the valley. But another type of glacier that we see are called ice sheets. And ice sheets are just gigantic sheets of ice. So these are not just found in really mountainous regions, but instead, our ice sheets are going to completely cover land. And the two largest ice sheets on our planet are Antarctica along our South Pole, and then Greenland off the coast of very northern Canada. So with these ice sheets, they're built on top of solid rock. So it's not just ice floating in the ocean, but instead we have continent with just very thick mounds of ice building on top of these solid rocks. But here there's so much ice that it completely obscures whatever is lying underneath them. So if we were to fly over Greenland, for example, we're just going to see a bunch of ice. We will not be able to see the rocks underneath it that's supporting all of the weight of that ice. But with our ice sheets, we're going to see that they flow differently from our valley glaciers. So since our ice sheets are generally forming on top of relatively top flat land, they're not going to be able to just flow downhill. If the land is flat, instead the ice sheet is going to flow outwards in all directions. And we'll talk a lot about it a little bit more, but we can also see that these ice sheets can get so large that they're going to start to grow outside of just where these rocks are themselves. So imagine that my little book here is all of the rock that's sitting underneath Antarctica. If just the surface or the top of my book was covered, the ice would be held up by the book itself. But we can also see ice shelves developing. And this would be as the ice had grown off the edges of the rocks supporting it. And instead, it's just flowing on top of our ocean water. But these ice sheets are going to be really important when it comes to our global climate around the planet. So we saw our last glacial maximum. The last time that we had a lot of ice sheets covering our planet was about 18,000 years ago. And here we can see an image of North America. And you should see that almost all of Canada and then a very good portion of northernmost United States is completely covered with ice sheets. So places like New York City were completely covered in ice only 18,000 years ago. But if we could switch to the other side of the planet, we would see that most of Europe and Siberia were also completely covered in ice. But our ice sheets are constantly advancing and growing out, and they're also retreating. They're melting and getting smaller throughout Earth's history. So we see that these ice sheets have grown and then melted numerous times over the last 2 to 3 million years. But when we're looking at our ice sheets, there are going to be some other things that are associated with ice sheets. So if we go into very cold ocean waters, we're going to see sea ice develop, which is basically just frozen seawater that's going to float on top of the actual liquid seawater beneath it. But here, the sea ice is relatively thin. With our ice sheets, we're talking about hundreds to thousands feet thick ice. But here, this sea ice is just very thin. Generally, it's going to be less than 10 feet thick. So it's much thinner, much smaller than our ice sheets are. But we're going to see that this sea ice, every winter when it gets colder, the sea ice is going to expand. That means more of this ocean is just going to be covered with a thin layer of ice because in the winter, the water's getting colder and freezing. But we also see that sea ice contracts every summer. That's because during the summer, these waters are warming. Therefore, some of the ice is going to melt, and it just means that there will be less ice overall within the ocean. But if we see that these ice sheets grow over the edges of the rocks that they're actually forming on top of, they're going to grow into an ice shelf, which we can see here. It's basically just a continuation of that ice sheet, but now it's not sitting on top of solid rock. Instead, it's sitting on top of seawater, so it's not going to be able to support the weight of all of this ice as well as if it had rocks underneath it. But eventually, with these ice shelves, if they grow large enough, they can completely break off through a process called calving and form glaciers. And then finally, we have a few other types of glaciers that just cover a lot less land than our other two. So we'll also see ice caps that develop, and these just happen in really high elevation environments. So basically where the elevation is so high that it's going to be cold enough for ice to develop and be maintained for long periods of time. So these are similar to our ice sheets, but they're going to be a lot smaller. But they're still building on top of solid rock. It's not just floating on top of the seawater. And then finally, we're going to see a glacier called a Piedmont Glacier that forms at the base of our valley glaciers, the first one that we talked about. If the valley glaciers are long enough, if they can go from the very top of the mountain all the way down to the base of the mountains where it starts leveling out again, if this valley glacier is capable of escaping out into this flat laying region along the base, we call this a Piedmont Glacier. And this is because the area at the base of a mountain range are called the Piedmonts. So here, our valley glacier has grown long enough that it's spilled out from the valley and is now on these flat Piedmont areas, forming a Piedmont glacier. But next, we're going to transition to how our glaciers actually move and why it's important that glaciers actually flow. So we'll see that glaciers move in two different ways. The first is called plastic flow. So here, imagine that glaciers are just like all of the pages stacked together inside of a book. I would be able to cause different layers or different pages of my book to be able to slide past each other. This is what plastic flow is. We're going to have some layers or some stacks of our ice be able to flow on top of others, while the bottommost layers aren't affected. They're just sitting there while other layers move on top of it. But we're also going to see that the entire body of ice, every single layer in the ice can also flow at once. So we're going to see that we have the entire stack of ice here slowly just flowing. Or we can have some layers that are going to flow or move on top of others while the bottom layers remain still. And that's called plastic flow. But when we're talking about glaciers, again, we're talking about massive thicknesses in ice. So there's going to be a lot of weight due to the amount of ice that accumulates. Therefore, we're going to see that the lower we go inside of our glacier, the more pressure there's going to be because all of the weight of this ice is just pushing down or compressing it. Since we have high pressures along the bottom of our glacier, that means that the top of our glacier is under very low pressure. This means that this ice is going to become very brittle. Think about something like peanut brittle, where you can just snap it in half. Because the upper portions of this glacier is so brittle, we're going to see that we're going to have really thick, deep cracks that develop in the top of our glacier. And these cracks are called crevasses. With this image, it doesn't look like much. But if we look at this picture of someone trying to get across a crevasse, we can see not only how long these cracks can be, but we can also get an idea of how deep they go. Some of them can be hundreds of feet deep. So if you were to fall inside of a crevasse, it would be very, very difficult to get out of one. So, unlike this person, if you ever get the chance to go trek over some ice in like Antarctica, don't ever try to cross a crevasse. Instead, try to walk your way around it so that you don't risk the chance of falling into 200 feet thick ice and not being able to get back out. But we want to be able to know how and how quickly our glaciers are moving. So we want to be able to measure the movement. And with our glacial movement, again, it's very, very slow. It might be moving maybe 5 or 10 feet per year at a maximum. So generally, the movement is too slow for us to just stand outside and watch it. What we generally do is just put GPS units inside of our glacier, and then every few months or years, we try to figure out exactly where it is inside of this glacier. But although most glacial movement is very slow, we could also see very rapid advances, where this glacier is just suddenly going to move downhill very quickly, which is called a surge. And this might happen if we just have an extremely cold year with a ton of snowfall. It's going to help that glacier slide farther down the valley. But when we are looking at our valley glaciers, we're going to see that the flow rate, just how quickly that ice is moving, is going to differ based on whether we're on the center or along the sides of our valley. So along the sides of our valley, this ice is scraping against solid rock. There's going to be a lot of friction that builds up as the ice and rock try to interact with one another. Just like if we rub up our hands, we're going to be able to very quickly feel the heat building up as friction. But here, the rock's friction is going to slow down the flow of ice along the edge. This means that all of the ice trapped in the center of our valley glacier is going to be able to move more quickly because it's just flowing on top of more ice. It's not trying to move on top of solid rock, creating friction. So we always see that our flow is the quickest in the center and then slowest right along the sides of our valley glaciers, where it's directly rubbing against solid rock. Since it takes so long for glaciers to flow, we want to create an annual budget. We want to figure out if that glacier is growing or if it's wasting or melting away over multiple years. So when we look at a single year, we see that almost every glacier is going to grow in the winter when we're getting more snowfall, and that almost every glacier is going to melt more in the summer when it gets a little bit warmer. So with our budgets for our glaciers, we want to look at it over longer periods of time than just a single year. We want to figure out whether we have more snow that's accumulating or if we have more ice that is melting or wasting away over periods of time. But when we look at our valley glaciers, we're going to have two different zones. We're going to have a zone of accumulation higher up in the mountains, and then our zone of wastage lower down in the valleys. So within our zone of accumulation, here we're just going to see more snow accumulating every year. The higher that we go in a mountain, the colder it's going to be. So the higher we are, the more likely that snow is going to stay there throughout the year and eventually be turned into solid ice. But as we go down the valley of our mountain, it's getting warmer and warmer, meaning that it's more likely that in these lower elevations with a higher temperature, all of that ice is going to melt or waste away. So the lower portion of our valley glacier is called the zone of wastage. But we're going to see that wastage can also happen along our ice sheets. So if we have an ice sheet that's just growing on top of open water, again, it doesn't have the solid rock underneath to support the weight. So if the glacier becomes large enough, that ice sheet is not going to be able to have its weight held up anymore. Instead, large chunks of that ice sheet is just going to break off and become an iceberg. So this image is just showing us again the differences between our zone of accumulation higher up in our mountain range where it's colder and more snow is going to basically be stuck there every year. And then we have our zone of wastage farther down towards the base of the mountain where it's getting warmer and some of the snow is going to start to melt. We're going to see that those crevasses, those really thick, deep cracks that form at the surface, almost always form in the zone of wastage because as that ice melts, it's releasing the pressure. Therefore, the ice is going to crack. But if we go to these really cold glacier regions, we're also going to see a lot of icebergs around. And if you've ever heard of the Titanic, it's what doomed that what was advertised as the unsinkable ship to actually sink. And that's because icebergs are just gigantic chunks of ice. But if we were to be in a boat going by an iceberg that might look like a small iceberg that we can navigate our ship around, in actuality, the majority of the ice in an iceberg is underneath the water, meaning that you would not be able to see it from a ship. And this is what happened with Titanic. They saw a relatively small iceberg along the surface. The captain was like, I've got this. I can just sail the ship around this. But what they didn't understand at the time is that about 80% of an iceberg is underneath the surface. It's not only deeper, but it's a lot wider than what you originally thought. So if you thought you had space here to navigate your boat, you would actually be running into the side of this iceberg, which is exactly what happened to the Titanic. The ice was able to basically destroy the sides of the boat. And as the boat tried to move past, the ice was able to dig in and just leave these long striations or grooves inside of the boat, allowing the water to get in and eventually sink the Titanic. But with our glacial budget, we want to know, is it accumulating or is it wasting? And again, we want to look at this more than just one year because every year we see that it accumulates in the winter and then it wastes in the summer. So with our glacial budgets, we want to look over longer periods of time, generally multiple years, if not multiple decades, to figure out exactly what's going on with this glacier. So if we see that over, let's say 5 years, that we see more snow accumulating as ice, then we have ice wasting away or melting. We're going to say that this glacier advanced. In the case of our valley glaciers that are going downhill, this just means that the glacier is moving farther down the valley, closer to the base of the mountain. But we can also see a situation where the amount of accumulation of snow turning into ice is going to equal the amount of ice that wastes away. This means that every year the amount of snow that's being deposited and the amount of ice melting is just going to equal each other out. So this means that the base of that glacier is going to be stationary. So we just call this a stationary terminus, where terminus is the end of the glacier. It's not truly melting or growing. But what we're currently seeing in most glaciers around the planet is that We have less accumulation every year, and we have more wastage, more melting than we have more ice accumulating. This means that our glaciers over long periods of time are melting more than we have more ice being deposited, which means that the glacier is retreating. So if we're talking about a valley glacier that's retreating, it's just a glacier where the end of it is just slowly making its way back up the mountain. Again, the higher that you go in a mountain range, the colder it's going to be, and the more likely we're going to be able to preserve that snow. But even in these areas where we see our glaciers are retreating, where they're melting very quickly, we see that ice is still flowing down the valley. But that flow is generally much slower than the rate of retreat. And we are seeing this worldwide today, especially due to climate change. And that's because glaciers are incredibly sensitive to temperature change. Currently, the Earth has warmed about zero point 0.6 degrees Celsius over the last 100 years or so. Zero point 0.6 degrees doesn't sound like very much, but glaciers are so sensitive that this roughly half a degree change has had a tremendous effect on how much ice we have on our planet today. So here we're looking at the same glacier at two different time periods. In the 1930s, we can see that the terminus, or the end of this glacier, goes throughout most of the valley. But if we go closer to today, we'll see that all of that ice has melted and now it's just liquid water. So we're seeing that right now our glaciers are melting and retreating at rates that we have never before seen, not only throughout human history, but throughout the entire history of our planet. So the book goes into great detail about a lot of the different types of erosional features that we will see over glaciers. But I'm going to focus on some of the major ones. So again, the book's going to go into a lot of detail, but I'm going to stick with the more generalized types of erosion, not only for the lecture, but for the quizzes and the exam as well. So just like a river, as glaciers flow, they're going to be eroding whatever sediment or rock that they're flowing on top of. But we're going to see that glaciers are very different than rivers because once they've started eroding these rocks away, the rocks can't just settle out like we saw big, heavy pieces of rock settling out towards the bed of our rivers. So once these eroded rocks have been actually broken out by a glacier, they're generally stuck inside of that ice until eventually it warms up and that ice melts. This is going to be important because glaciers are capable of moving huge chunks of rocks. We saw in our last chapter that rivers can move basically pebble-sized pieces of rock for the most part, unless it's flooded and the water's moving incredibly quickly. But glaciers can move chunks of rock that are, close to the size of a football field. We would never see a river being able to move a rock that large because of how much energy it takes. But because rocks get stuck inside of glaciers, these glaciers are going to be able to move very large pieces of rock. So if you've ever been to Central Park in New York City, you might have noticed these huge boulders that are just randomly located throughout the park. And these are actually really interesting rocks. Up until about the 1970s, geologists had no idea where these rocks actually came from or how they got to the middle of Central Park because they were a type of rock that's not found within the entire state of New York. They later found out that these glaciers were able to carry down large chunks of these rocks from very northern Canada during our last ice age. And then as the ice melted from about 18,000 years ago to the present, that the ice was dropping out these giant boulders, and they were just left in the middle of Central Park. But we're going to see that glaciers erode the rocks that they're moving on top of in two different ways. The first is called plucking. So as this ice is flowing on top of the rocks underneath it, we're going to have the ice itself being able to break apart the rocks into smaller pieces and literally just be able to pluck them off the surface. But we're also going to see something called abrasion that happens. And with this, think about using sandpaper to sand down like a table. We're going to have very small pieces of rock called rock flour. And here, as this rock flour moves across the solid rocks beneath it, it's basically just going to sand it down as if it were sandpaper. So it's going to leave a very flat, smooth, and generally a very well polished or shiny surface. But if we have those really large rocks, like we saw with the ones left behind in Central Park, those larger rocks are going to form something called a glacial striation. And we talked a little bit about this when we were talking about Wegener and some of the evidence that he used to support his idea of continental drift. So glacial striations are just going to be these deep scratches in the rock. So if we have our solid rock and then our glaciers that are moving on top of it, if we have some jagged pieces of rocks, they're going to be able to dig inside of this rock and form these deep scratches as they flow. So the direction that these scratches or these linear features are going is just going to tell us basically which way these glaciers flowed. And we can see both polishing from abrasion here. We'll see that this granite is incredibly smooth. It's also very shiny because it has a polished surface from all that rock flour that basically grinded away or sanded down the surface of this rock. You'll also see some of these long linear marks. These are glacial striations, but it's a little bit easier to see here in this image on the left. You'll see these long marks that are basically going from the top to the bottom of this rock. These scratches are telling us that the glacier flowed in this direction. We always know that they flow downhill for the most part because gravity is slowly pulling them down, but we can use the exact location of these scratch marks to know exactly how that glacier flowed in the past. But we're going to see that how much glacial erosion happens as the ice slides across the rock is going to be dependent on a lot of different things. The first of which is just how quickly is this glacier actually moving across the rocks. The faster the ice is flowing, the more erosion will happen than if it were slower flowing. But the thickness of our ice is also going to be very important because the thicker the ice is, the more it weighs. That means that thicker ice is going to be pressing down on the surface of our rocks more, meaning that we're going to have more erosion from all that added pressure. But if we have a very thin piece of ice, here we don't have a lot of pressure. So we see that as we increase the thickness of our ice, it's adding more pressure to the rocks beneath it. And therefore, it's going to be able to erode those rocks beneath it more the thicker the ice is. But since we have these solid rock fragments that are stuck inside of our glaciers, we want to think about the shape of these rocks. If they're totally round like a ball, they're going to cause erosion of the rocks beneath a little bit. But if they're very jagged in shape, they're going to be able to dig down and leave scratches in the surface, therefore increasing the amount of erosion. But the abundance, just how many of these rock fragments, as well as the hardness of them, are also going to be important. Obviously, if you have a lot more rocks grinding into the rocks beneath it, you're going to see more erosion. But the hardness is also more important. If we have igneous rocks that are stuck inside of this ice, those igneous rocks are generally the hardest rocks on the earth. They're going to cause a lot more erosion than softer rocks like limestone. But finally, we want to look at what kind of rocks are actually sitting underneath the glacier. If we have, again, like an igneous rock that's really difficult to erode, a lot of these previous factors are going to be less important because that harder rock sitting underneath our glacier is just going to be harder to erode. But if we were to look at, let's say, a limestone sitting underneath this glacier, with limestones, I can easily pull out a hammer and break it apart. So we're going to see that softer rocks are going to be eroded a lot more easily by glaciers than our harder rocks are. Then we're going to end this chapter talking about how ice on our planet has changed over geologic time and end up talking about what we might expect in the future. So during our last glacial maximum, which again was about 18,000 years ago, we saw that about 30% of our planet was covered in ice. This had some very major effects. The first of which is that it forced animals to migrate. If animals were living in, let's say, Canada, and now all of Canada is covered in ice, these animals either have to migrate south or they're going to die out because they no longer have access to liquid water to drink or forms of food, especially if they eat plants. So we see that there are major migrations of all different types of animals when we have more ice on our planet. But we also see that ice weighs a lot. So when we had glaciers covering large portions of North America, the glaciers were so heavy that they forced the land farther down with it. As these glaciers began to melt or get thinner, we see that the land's going to rebound. It's going to start moving upwards. And this is an issue if you live in like Michigan. If you buy a house in Michigan, you might see that the foundation of your house will crack very easily. And that's because Michigan used to be completely covered in ice 18,000 years ago. But as that ice has melted, now the land is rebounding. It's going higher up, meaning that your house is also moving upwards. But we also see, especially in areas like Michigan, that as these massive ice sheets begin to melt, which we call meltwater, that liquid water has to go somewhere. And it formed proglacial lakes. Basically, the glaciers melted and it formed new lakes. So if we're to look at the Great Lakes around Michigan, we see these massive lakes that we can easily see from outer space. These lakes were not there before 18,000 years ago. And that's because they're proglacial lakes. They formed as that ice began to melt, and all that melt water just went to a very low-lying area, forming these gigantic lakes. But just like we're seeing these Great Lakes forming after the ice has melted, we're going to see that our streams change their paths as well. So this bottom image are major rivers um, before our last ice age. But this upper image is what it looks like after the Great Ice Age. So here we can see that some of our rivers remain mostly unchanged, but some of our rivers are going to totally change their path. So we look at the Mississippi River, for example. If we look at it before the last ice age, it was relatively short. But now our Mississippi River cuts through two additional states. It's grown in length after all of that ice melted. But we're also going to see that some rivers are going to drastically change their path. If we look at the Missouri River, we used to have two separated Missouri rivers. We had a lower one and then an upper Missouri River. But as all this ice melted, turning into meltwater, the meltwater always wants to escape in the easiest path. I like to say water is lazy. It wants to take the easiest, quickest way out of an area. So as all this ice was melting in the upper United States, it caused the upper Missouri to join together with the lower Missouri River, forming one gigantic river system today. But one of the major things that we saw with our last ice age was that because so much ice was trapped on side of our land, it caused sea level around our world to drop very significantly. So when we usually have our oceans, they're full of liquid water. But all of this ice, the water is stuck inside of it, meaning that it can't go back into our oceans. So 18,000 years ago, global sea level was about 330 feet lower than what it is today, or the equivalent of 33 stories in a building. This significantly changed the coastline, not only the US, but all coastal regions. So this black line is showing us our coast today. But if we were to be able to look at what our coast was like during our last ice age, we'll see that our coastline actually extended farther outwards than our oceans. If we look at Florida itself, because sea level dropped 330 feet, now the size of Florida is over 2 times as big as what it is today. So we see that the amount of glaciers on our planet has a direct tie to our sea level. More glaciers mean that we're going to have lower sea levels. We're going to have more land exposed. But what we're seeing today on our planet is that our glaciers are very rapidly melting. This means that all of the water that used to be stuck as ice in these glaciers are now melting and returning to the oceans, meaning that our sea level is rising across our entire planet. So, over the last 2 to 3 million years, what we call the Quaternary period, in our historical geology, we see that there's a lot of periods of time where our ice sheets expanded and grew, and there are also periods of time when it retreated, melted, and got smaller. And this is going to be particularly important when it comes to the Antarctic ice sheet. It's over 10 times as old as this Quaternary period is, but it's been around fairly constantly throughout this period. There are just times where it grew or shrank more than others. So we see that during our last ice age, 18,000 years ago, here we see that it's not just Canada and Greenland that's covered in ice, but large chunks of the United States, as well as most of Europe and Siberia as well, were just trapped underneath really thick formations of ice. So we see that almost 30% of all of the continents were stuck underneath ice during our last ice age. But in the last 18,000 years, we've seen that that ice has been melting away. Now, if we go to Canada, it's not a barren ice field, but you're actually going to see some relatively nice green areas. So naturally, we do see periods of when ice is going to expand when it's a little bit colder. And we're also going to see periods where the ice is going to retreat and get smaller when the earth has warmed a little bit. But this is very different than what we're seeing today. Right now, climate change is having a significant impact on the glaciers around the world. We're seeing that climate change is happening because we are burning fossil fuels. We're taking all of these carbon rich liquids and solids from underneath the ground, we're pulling it back up to the surface, and then we're burning them, whether it be the fuel in our cars or coal being burned to form electricity. We're burning all of this carbon, which means the carbon is going to be re-released inside of our atmosphere instead of staying trapped underground. We really started burning our fossil fuels in about the last 150 years. And during that time, we've started seeing massive changes in our climate. Today, we know that this massive and very rapid climate change is occurring because of us. Humans love fossil fuels. So the more that we burn, the more that our entire planet is going to heat up. So this image is showing us Greenland, and the different shades are showing us how much ice is on top of this land over different periods of time. This light pink color is showing us how much ice sat on top of Greenland in 1992. We fast forward a few years, and this red is showing us how much ice was there in 2005. This white area is how much ice was left in 2012. So we can see that within about 20 years, how much ice Greenland has lost. And we'll see that as our planet continues getting warmer, we're going to start losing this ice more and more rapidly. I would recommend that you look up February's snowmelt in Antarctica. There was one day this past February where Antarctica got up to something like 75 degrees, which is incredibly hot. It's going to melt a lot of the ice. And during just a 1 week period after that one warm day, they saw substantial changes in how much snow was left on top of Antarctica. So we're going to see very massive changes, not only in how much glaciers we have on our planet, but where our sea level sits. As more glaciers melt, our sea levels are going to rise. And we're going to start seeing the effects of that sea level rise, especially in places like Florida, where we're right along the coast. In places like Miami or Tampa, they might be completely flooded. But even in Orlando, which is in the middle of our state, we're going to start seeing other impacts. We might start seeing more droughts. We might see a change in our rainy season. But more importantly, what we're currently seeing are changes in our hurricane seasons. We're seeing not only more hurricanes every year, but they're getting stronger and stronger. But with climate change, we're going to talk about this a lot more in future chapters. So stay tuned.